Hi everybody, welcome back to Calculus 2 through examples or by examples. We're going to start section 2 now on integration applications. So the first application we're looking at is finding the area between curves. I want to emphasize here some of the ideas that I talked about in the video on Riemann sums and on other review topics. This idea that you technically start by approximating what it is you want to solve, and then you refine things until you get to a continuous result that gives us an exact answer. Okay, so here I'm trying to find the area between the function f of x, which is the blue function here, the curve on top, and this line g of x. I envision this with the little rectangles that I would have drawn when we had a Riemann sum. So if you haven't watched the video on Riemann sums, you might want to go back and do that. So I imagine that this region, this filled in shaded region that I'm trying to find the area of, I think of it as being broken into a whole bunch of little rectangles, and that I can find the areas of the rectangles because the area of a rectangle is its width times its height. Since the bottom corner of the rectangle is on the function g of x, and the top corner of the rectangle is on the function f of x, its height is f of x minus g of x. So I take the height of the top corner minus the height of the bottom corner, and that gives me the height of that rectangle. I multiply that by the width of the rectangle, and the width of the rectangle is delta x. It's the width, it's the change in x. It's how big your little step is. So each individual rectangle has area f of x minus g of x, and then you multiply by its width. When you add those up, if you imagine that there's lots of little rectangles like there were when we looked at the Riemann sums, when you add up all those little rectangles, that gives you an approximation. We then take the limit as the number of rectangles goes to infinity and the width of all the rectangles goes to 0, and that turns it into a definite integral. And that definite integral is how we find the area between the curves. All right. So once again, I want to emphasize this idea that a lot of what we do in calculus is we start by making an approximation of what it is we want to find. So in this case, we imagine dividing this area into lots of little rectangles like we did with the Riemann sum. Then we refine that approximation incrementally. In this case, it would be my making all the rectangles thinner and thinner and thinner so that we have more and more of them to get a better and better approximation. And when we take the limit of that process, we get this definite integral, which will give us the area exactly. Okay? So this is how we can find the area between two curves. And this isn't a specific example, but it does give you the idea of how to approach this. Okay. Now here are the specifics. The function on top, the f of x, is 2 minus x squared. It's a parabola. The function below is x. So I take the 2 minus x squared and I subtract the x. So this represents the height of my rectangles. And the dx represents the width of an infinitesimally or infinitely thin rectangle. And remember that the integral sign represents summing up all those infinitely thin rectangles with the rectangles starting at 0 and going over to 1. This evaluates to, using our antiderivative rules, evaluates to 2x minus 1/3 x cubed minus 1/2 x squared. We evaluate between 0 and 1. We plug in 1 and plug in 0, and we subtract what we get when we plug in the lower limit of integration from what we get when we plug in the upper limit of integration. And that leaves us with an exact answer of 7/6. So the first two lines here are the general idea of how you should approach these problems, and the rest of it is just this specific case. Okay. So in the next video, we'll talk about finding volumes, and I'll see you later for that.